exercise 2, we will now talk about pruning. In 2a, you should describe what is cost complexity pruning. So, like linear regression, a card model, which is classification or regression tree model, is prone to overfitting when model complexity exceeds a certain level. While for linear regression, complexity is given by the number of parameters, it is given by the number of splits or the depth of a tree for card models. Okay, so it's the more splits you have, the more branches your tree has, the more complex the model gets and the more regions you will end up with. So the more terminal nodes you will have in the end. And if you think about it, if you would just grow out a tree completely, this would lead us to have one region for every terminal node. And this is complete overfitting. So we have to find something in between. So basically between the only root node prediction and the one region for every single observation prediction. So let's see. Here, also like linear regression, card models can be penalized for complexity in their objective or loss function. However, this penalization term works differently. It penalizes the number of terminal nodes in a tree and therefore the number of branches or splits inside the tree. Yeah, logically, after every split you take, there will be more terminal nodes. So split the root node once, you will end up with 2 nodes. Split each of them once, you will end up with 4 terminal nodes, and so on. So you can penalize that, and we see the objective function here, or the loss function. And I think we also call it optimization criterion in the lecture. So this is all basically meaning the same. Maybe I should at this point tell you that once you calculate this criterion, you can also call it a loss. Okay, so if I have a metric which describes the loss, I can use it as a loss function. There's still a slight difference in that. So a loss function is also always used as the objective function for a optimization of a model. And if I calculate then the loss, or if I use the values from my model to calculate the value with this loss function, I will call it a loss. And I can measure also loss in form of a metric like MSE or RMSE as we did before. So just to mention that, because I think I will often use the term loss in this context, and just so you know what I'm talking about. Okay, so the tricky part, or let's first say what is the penalization term, it is this last term, which consists of this alpha value, which is a parameter, and this t in absolute. So this is the number of trees here. Describes the number of trees. Okay. The tricky part about this objective function is to find this parameter alpha, which determines the degree of punishment due to the model complexity. So if we have a high alpha, then we will punish the number of trees very heavily. But if we have a lower alpha, then we might not punish it enough, and then this will lead to overfitting again. So that's a tricky part, and we have a way to determine a good value or maybe an optimal value for alpha with cross-validation. which we will use for several values of alpha. And then we choose the alpha which minimizes the out of sample error. Okay, and here particular the cross-validation out of sample error. So I could actually correct this here. Exactly, so that's the description. What cost complexity pruning is. You reduce the size of the tree using a penalty term for complexity. Now, let's come to exercise 2b, where we will apply this cost complexity pruning. And for this, I used a different data set, as the Diamond's data set is not optimal for this purpose. I won't go into details to why this is, but it is very hard to actually show the relationships that I want to show. It's kind of special in that sense. So we will go to use another data set which you can obtain from the source. So the data set is open source, provided by the UCI machine learning repository, and you can just click on data folder and download the data. After you've done that, we will only use one part of the data, which is the student math data set. There's also another one, but yeah, we won't use it. You can play with that if you want to. It's basically structured the same way. So we will use G1 as a target variable, which is one grade of students, and the grades measured in points between 0 and 20. And we will delete G2 and G3, as these are different grades, and we would not want to include them as predictors, because obviously they will be heavily correlated. Now we can build our model using the remaining variables as features, and then explain what we're doing. This is the reference of the dataset, just to let you know. So let's start. First, we need our libraries again, which you're already familiar with. Then we will read the dataset. Or let me just restart and clear the output, so we can do this step by step. Might take a second. Okay, now let's import the libraries and read the dataset. I have to call the separate. I have to change the separator here, as normally it would be just a comma, and it is a semicolon in the used in this CSV file. So you need to change the separator afterward, otherwise it wouldn't work right. Yeah, let's have a look at the data. So we see our variables, not all of them, but most of them, and we see our targets here. So let's get a better view on the structure. Now we can see all of them, and we see there are a lot of factors in here, so categorical variables, and also a lot of integers. Well, as we know already, categorical variables are no problem for us, and we will continue. So here again we can see the column names. Now we will delete the targets G1, G2 and G3, as we only want to have G1 as target and all other variables as our features. I could quickly mention, now this is obviously a dataset I use to demonstrate the procedure to you. If you would, you could also just use these grades as categories from 0 to 20, as there are no steps in between, so it's not continuous. It's basically also categorical. However, it also works in a regression tree, and we will see even better than in a classification tree, or at least for the purpose I will demonstrate. So let's continue to build this regression tree. Exactly, we said already we want to use our pruning mechanism, and we need to search for an optimal alpha to have the right value for our cost complexity pruning. So we will set CP to 0.001, which is a very low value. So it will search for, or we will use all the alphas, the feasible alphas, within the range from 0.001 to 0.1. And so this determines the lower part. And we will set xval to 10, which determines the number of k in k-fold cross-validation. So it's a 10-fold cross-validation. Now, if we use PRINCE-CP, we can actually have a look at the results. So here we have a lot of a good overview of the model, and here we see the actual different values for alpha and the related statistics for the cross validations. So as you know, the relative error here is in-sample error, and this is actually the X error is our out of sample cross validation error. So the average of all cross validations out of sample errors. So this is our relevant metric here we use for choosing alpha. We want this to be as low as possible, and as the professor already told in the lecture, this is not monotonous. So at some point it will, so first it declines, and then at some points it will rise again, and we want to find the optimal one, which is here at 5, or at 5 split, sorry. So it's this is the out of sample error, the CV out of sample error. This is the alpha that led to this smallest error. So as the professor already told you in the lecture, we won't use all values for alpha between the one we chosen here, 0.001, and the maximum, which is the maximum is always that value, in our case here 0.1, which will lead to the root node. So this is the maximum punishment. And yeah, so why did we use, or how do we get to these alphas? This is more complex. We won't go into detail right now. I think the professor already said a few words of how you get to these alphas, but basically you need just these alphas because the range between two alphas will always produce the same tree in the end. So let's say between here 0.015 and so on, and 0.022 and so on. The range between that, it will always result in four nodes, 4 splits. I mean 5 splits. So from this point on forward, it will result in 5 splits, and once this alpha is reached, it will be 4 splits until this alpha is reached. So the whole range between that will produce 4 splits and so on. So I think you understand what I mean. So we will choose the lowest out of sample error, which is at an alpha 0.01 and so on. And now we'll build our regression tree using this alpha. Okay, and yeah, I won't go into details because we haven't discussed all of the variables in here. But this is basically how you can end up with a pruned tree. So let's discuss variable importance, which is exercise 2C, which won't take long. So we want first to have our normal variable importance of the upper tree here, and then the one in percentage. So just use your model name and then dollar variable importance, and you get the variable importance, and we see that failures is the most important variable used in this tree here, and then come the remaining variables here. So to put it in percentage, we can just divide it by the sum of all variable importances, and then we see that failures is responsible for 27% or 27.4%